Antony Bahri. Tony. Que nos va a hablar en inglés sobre la información oculta en un producto cartesiano. Tony.
No, sorry. I don't know what's a good question. Well, the answer to some no, because there's instruction. I don't know what the I know that that's just the first part. I don't know. My guess is that yes, I need my slides.
Okay. Well, once again, I'm grateful for this opportunity to take part in this celebration of my friend and colleague, Samuel. I am going to discuss Sam's recent work, the last 10 years, with my colleague Martin Bendersky, who just spoke, and my absent colleague, Fred Cohn. And it has been the most wonderful collaboration. Sometimes I wonder whether we do mathematics simply to express our friendship. Well, Martin and I, and screaming at each other as we do, doing mathematics, it's hard to tell that we are friends sometimes. But I'm very grateful to have had this opportunity to work with Sam so closely. And my goal is to just give you an overview of some of this work and some idea of the extensive application which the work has enjoyed in the mathematical community. Now, I must thank Joseph and Anna Rosa Cohn, very good friends of Sam, for helping me to translate my lecture into Spanish. So in many ways, I was quite intrigued by Alejandro's lecture, whose first diagram is very similar to mine, who used two jokes, which I understand to be the same as mine, and dually, he has showed English slides and spoke in Spanish, but I am going to show Spanish slides and speak in English. If I can get to it. Now, the first thing which I wish to discuss is an operation on sets, a very elementary operation in mathematics. And this operation, it is called the Cartesian product, named after René Descartes. And it said, and the construction takes two sets, A and B, and it gives me a new set, which we call A cross B, a new set. And this new set consists of all the pairs A, comma B, satisfying the property that the first entry is in the set A and the second entry is in the set B. But not every set is a Cartesian product. Here is a picture, and this set, which is colored, it is not a Cartesian product, because if it is an A cross B, then because x2, y2 is in the set, x2 will be in A. And similarly, y1 will be in B. So therefore, x2, comma, y1 will be in A cross B, and it is not. So not every set is a Cartesian product. Now, Cartesian products have shape. They have geometry. For example, the cylinder at the top, it is the Cartesian product of a circle with a disk. And below it, we see the example that we have seen all day. But this torus, it is a Cartesian product. It is the Cartesian product of the circle with the circle. Now this diagram I leave this as an exercise for homework, right? Is the set at the bottom, is it a Cartesian product, right? The question better asked is there such a set? And Martin will be very interested in the set at the bottom. And I will tell you why Martin will be very interested, and you can ask him more about it later. But Martin, the set at the bottom was the motif for the Australian production of Wagner's Ring Cycle in Melbourne. And now, I wish to talk about another object in mathematics. I have talked to you about the Cartesian product, a geometric construction, in the sense that I'm going to use it. And the second thing I want to talk to you about is a very important object. And to say what it is, I must introduce mathematical symbols. And this object is going to be called a simplicial complex. And the simplicial complex is a combinatorial object which is defined beginning with a set of vertices. Now, every set has what is called a power set, and that is the set of all subsets of the set. So I give you a set, and you look at the collection of all subsets, and that is called the power set of the set V. Now, the set which I wish to describe, it is called K, and it is a subset of the power set. So it is a set of subsets of V, which satisfies a special condition, and that condition is if there is a set sigma in K, then all of the subsets of sigma must be in K. And here is an example. V is V1, V2, V3. Here M is 3. And K consists of these sets. The empty set, the set with just V1, just V2, just V3, and then the set with V1, V2, and the set with V1, V3. And we can see that every subset of every set in K is also in K. And that is an example of a simplicial complex, or more precisely, an abstract simplicial complex. Okay. And the advantage is, and I'm not going to go into the details of how we can do it, but we can draw a picture of a simplicial complex. And the previous one, you can see this will be a picture of the simplicial complex. You see the V's, they are just the dots. One dot for each V, which was in the simplicial complex. And then we had V1, V2 in V, so that is an edge. And then V1, V3 is in V, and that is an edge. So this is a picture of a simplicial complex. Now, if the simplicial complex is the whole power set, the set of all subsets of the set, then the picture we get is completely filled in, because every edge is in the set, every vertex is in the set, and the whole triangle is in the set, V1, V2, and V3. And we call this special simplicial complex a simplex. So a simplex is the maximum simplicial complex. And you can see that the top is a piece of the bottom. It's just a piece of the edge. Right? So I cannot, if I only have 3 vertices, I cannot have a bigger simplicial complex than the simplex, the one at the bottom. Now, I want to relate simplicial complexes to Cartesian products. I have told you what a Cartesian product is, and I hope I've given you some idea of what a simplicial complex is. And now I wish to make something geometric which combines combinatorial information with geometric information. The combinatorial information comes from the simplicial complex. The geometric information comes from a family. Actually, I love the way that Sam used to say the word family. But I'm just reminded of it as I say it. I don't say that word with the same eloquence that Sam does. A family of geometric pairs, xi is a geometric object, and ai is a geometric object, and ai is a geometric object inside xi. So I will give some examples. This is supposed to be in red, but anyway, here are some examples that are very important in our work. xi is a disk, one-dimensional interval, and ai are the boundary points. xi is a two-dimensional disk, and the ai is the boundary circle. And the next one is I take the circle, and then the A is just the top part of the circle. Now these look like very simple geometric objects. It is true, they are very simple, but they contain a lot of very complex mathematics, and they have wide application. Now, I listed here some other examples. I will not describe what they are, but these other examples are for the experts. The experts will understand these other objects and their utility. Okay, so now I have told you I've told you the definition of a Cartesian product, geometric object in our world, and a simplicial complex, combinatorial object, and I have given you some examples of the geometric object, the pairs of spaces. I need three things. These pairs of spaces are going to be related to the Cartesian product. So now, with this information, combinatorial information, geometric information, I apologize for the mathematics symbols, but the symbol on the left, the ZKXA, this is the geometric object which I am making. I am making a new geometric object from the K and from the XA, a new geometric object. And this geometric object, it lives inside the Cartesian product of x1, x2, up to xn. And I will make this object in such a way that if the simplicial complex is the empty set, as small as possible, then this new space will be just the Cartesian product of the A's. This is the extreme. And if the simplicial complex is everything, the power set, the simplex, then this new space will be the Cartesian product of the big spaces. So every possibility will fit between the top and the bottom. And there is and the moral of our work is there is a lot of geometry between the top and the bottom. That is the point I want to make. I will tell you the rule for making it. This is my one luxury. To make this space, this ZKXA, it is made from Cartesian products, right? You take every sigma in K. So sigma is a subset of the set of vertices. And I make a Cartesian product. Length is the same as the number of vertices. yi is xi if I is a vertex in sigma, and yi is ai if I is not a vertex in sigma. And so the space I define is the union. I just combine everything. I combine everything to make this space. And for the experts, in many important cases, these spaces are manifolds. And so we call this space now, in the literature everywhere, it is called a polyhedral product. A very apt word, and it was invented for us by William Browder, from whom we heard earlier. And William Browder is the inventor of the term orbifold. So this phrase, polyhedral product, it has a distinguished pedigree. Now, I will give you an example. So here is an example. I just take M is 2 vertices, and the K is just the 2 vertices, right? It's not the edge, just the 2 vertices. So in this example, I want to take the XA to be the interval and the 2 points. You see there, I've drawn the interval D1 and the 2 points S0. So I take the first simplexing K, V1, and it gives me D1 because V1 is in sigma, and the blue S0 because V2 is not in sigma. And the second one, V2 is in sigma, so I take the S0 from the first one, and V2 is not in sigma, so I take the S0 in the first one, and V2 is in sigma, and so I take the D1 from the second one. And then you see each piece, 2 intervals, but in different order. And when I make the polyhedral product, I combine the 2, right? So when I combine these 2, you see, I get a square. Now, unfortunately, the color is not appearing, but the polyhedral product is the square on the left, and it is inside the filled-in square. It is the boundary of the square. Unfortunately, the color did not come. Okay. So here is another example. This time I take 3 vertices. I take my simplicial complex to be 1 edge and 1 vertex. And I take my pair to be the 1 disk and the bounding points. And this time, I will get a polyhedral product which is inside the Cartesian product, interval cross interval cross interval, which is a cube. And you see, I get this bed, the bed with the canopy, right, inside the cube. So this is a non-trivial example, by the way. Now, these appear, this polyhedral product has been applied in all these fields of mathematics. So you can pick what you like here. Our free groups have been analyzed, the classifying space has been analyzed to the wazoo. If I take an odd sphere and a point, I get quadratic algebras, complements of subspace arrangements, but most importantly for us, the first example, the 2 disk and the circle is at the center of the topological approach to what is called toric geometry. And that is a field which has had a lot of attention. Now notice the second one, it says number theory. Number theory. See, the disk and the bounding points, the interval and the bounding points, has applications in number theory. And I will show you, I hope I will be able to show you briefly. Okay, so I want to tell you a property of the polyhedral product which is a miracle. If I have 2 pairs of spaces, XA and YB, in mathematics I can take the Cartesian product of the pair and I get a new pair where the first entry is the Cartesian product of X and Y, and the second space, the new A, it is a union of Cartesian products. But the important point is that I can take the Cartesian product of 2 pairs. Now, if I can take the Cartesian product of 2 pairs, if you give me a string of integers, J1 to Jm, then I can exponentiate, right? I make a new pair, YIBI, to be XIAI raised to the Cartesian exponent Ji, exponential, right? Now, the important point here is this is completely geometrical. So I start with geometric spaces at the top, and I make new geometric spaces at the bottom. I have taken a string of integers, and I go from one geometric space to another. geometry. There is no combinatorics here, seemingly. But by a miracle, which I do not understand still, by a miracle, and it's our joint work, there has to be an operation on simplicial complexes which takes me from a small simplicial complex to a large simplicial complex, k of j. There has to exist. Now remember, this has never seen the exponentiation of pairs. And this operation on simplicial complexes must exist in order to ensure the following identity. That if I put the k with the yb, and I put the original xa with the kj, then these two polyhedral products are identical. Now, those of you who have been following very carefully will say that, Tony, the kj xa cannot be defined because kj has more vertices than m, right? But what I do is I simply introduce multiplicity. So xij ai appears ji times. Now this looks a very simple result, but it has a lot of consequences in many fields. Because, and this combinatorics that came from nowhere by a miracle, right? By a miracle. And here is some applications of this idea, and this is just a selection. And by the way, just as before I got on the plane to come down, I opened a paper of Limonchenko, and there is another application right there, just on my way down. So, and this is not a complete list of applications of that simple idea. Now it looks like there was nothing there, but look at the fields of mathematics where this work of Sam and his collaborators has produced these dramatic applications. So, okay, I have another page of mathematics. I ask you to forgive me. It expresses, I make the same appeal as Martin. The mathematical symbols here, which are very complicated, they express a very simple idea, right? A very simple idea. Now, as topologists, we wish to understand what is the geometric shape? What does the polyhedral product look like? We want to answer this question. What does it look like? It is a very complicated space, and in one of our joint papers, we show that the polyhedral product, zk x comma a, it breaks into very simple pieces, pieces which we can identify. So complicated breaks into simple pieces, simpler pieces. This is very important. So the left-hand side, it is difficult, and the right-hand side, it is easier. And that fact leads to many applications of this theorem. So that at the bottom, I say in general, the spaces are much simpler geometrically than the original space. And that is the power of this theorem. I know it is in complicated symbols, but it says something very powerful about the geometry of this polyhedral product, which is enjoying such wide application. Now, this is technical, but I cannot help myself from introducing this for the experts. It's technical, but this is the application of this theorem to number theory. Remember, we are doing geometry, topology, and combinatorics, and now we have number theory. Well, a student of Fred's, Ali al-Raizi, he showed, and Martin, you recall Martin used the word homology. Well, he showed that this decomposition, this structure theorem, it behaves well with respect to homology. And now I apologize, I'm making comments which only the experts will understand. Please forgive me. This, in homology, this is equivariant over the automorphisms of K. Now that is a very shocking result, right? It makes no sense that this should be. Generally, we are looking at actions on the spaces X and A, but here we're looking at the action of the automorphism group. And so he shows this is equivariant. Now by taking K to be the boundary of the n-gon, right? The simplicial complex, which is the boundary of the n-gon. And by considering the dihedral group, so I'm just going to consider a cyclic subgroup of the dihedral group, which is the automorphism group of the n-gon. Right? So I'm going to consider a cyclic subgroup. So he obtains an interesting result in number theory. And he says, so you just look at H2 of the polyhedral product, the second cohomology group, and you look at it as, you look at a basis, you find the total number of orbits arising from basis elements of H2 as a Z of Cn modules. Cn is the cyclic group. And he counts these orbits using n-beaded necklaces, two colored n-beaded necklaces, and he gets a formula involving the Euler phi function. Fair enough. He does another count using primitive necklaces. And this time, if you start counting primitive necklace, the Mobius function appears. So if you count the same thing two different ways, the answers are equal. And sure enough, he gets this identity between the Mobius function and the Euler phi function. Now, this is from Cartesian products, right? Now, it turns out that the number theorists knew this result. They knew it. But their techniques for proving it were not as direct as these geometric and combinatoric ones. And I just put there that the Euler phi function appears in K colorings of an n-beaded necklace. And now here are applications. Now I'm just choosing two theorems from the work that Sam has done with us. Just two theorems. And look at all the fields of mathematics here to which this has been the different applications of this theorem, and this is not all of them, right? This is just some subset that I thought up in what time that I had. But, there've been arachnid mechanisms studied, there've been robotics. 1 year, Sam showed a movie of a spider, a mechanical spider crawling along using this theory. And so there are algebraic applications, cohomological applications, homotopy theoretic applications, and applications to free groups for studying monodromy. I could just go on and on, but I don't have time. Okay. So I have illustrated two theorems from our joint work. But our joint work extends. Sam's mind is very restless. Now, what you see here is a page of Sam's notes that he sent to us. And Sam, this was very late. This is very late, Sam. And here, he learned a new idea from the combinatorial theorists, associated to any monomial ideal ring, there is the Avramov lattice, and there is a graph. And Sam wanted to understand, he had this theory that related to these JIs. Remember I told you about the JIs and the exponentiation? He had a theory. Excuse me. Oh, I might go back to the last slide. So he had a theory which was going to tell us that if I had two sets of combinatorial information and these lattices and these graphs were isomorphic, then the geometry of the polyhedral product was the same in a certain sense. This is a very powerful theory. Now, there's at least one paper in these ideas, and we ran out of time. It's a very powerful idea. I picked a page that was readable, but many of the pages are scribbled out so much that they're not readable. I meant to say, anyway, I passed up that. Sorry. So this is toward the end. And now, of course, you know, as a group, we like to be aware constantly of Rachel's role in our work and good friend that she was to us all, and the support. You know, a strong case could be made for the fact that Rachel's support of Sam helped his mathematics immensely. It was so clear to me. So I may have misattributed this photograph. It's in Bill's house, Bill Browder's house. It may have been taken by Lisbeth Muller or John Davis, I'm not sure. But actually, you notice there that I have Muller, M, and then the Danish 5. You see in the name, the Danish 5. I did not know how to do this in tech. So I put into Google, I put in to find out how to make the Danish. So I put into Google, Danish accents in LaTeX. And I clicked the button, Danish accents in LaTeX, and I clicked the button, and up came, the first thing that came up was images. And the images were of the Danish symbols. Right? But as I scroll down, it turns out I discovered that Google does not pronounce LaTeX the way mathematicians do. Google pronounces LaTeX as latex, which is a rubber material. And there followed images of Danish models in these very tight latex dresses. So, you know, you've got to be careful when you do text search. You know, there it is. So with that photo, I extend my gratitude to Sam, to Rachel, and to all of our Mexican friends and colleagues. And I thank you for the opportunity to say these things about Sam. Thank you.
Any questions? ¿Alguna pregunta? Bueno, pues agradecemos a Tony y su conferencia.